for today, I just prepared basics. Yeah, so I will not come up to the details of inorganic chemistry because we have a lot to discuss over there, and that may just a little bit over the scope for one meeting. But I would like to, what I would like to do today is to really talk about the general basics of InChI and what the InChI wants to achieve. Okay, let's start a little bit with the history. You see, it's already pretty old and it's linked with mass spectral databases. The important part over here in the history is are the blue sections, because the structures or compounds behind that one were identified by CAS numbers in the beginning, but in 1998 the CAS contract was not renewed because of costs, and they had to find something else to identify the compounds. Yeah, so the primary reason the InChI is in the world is an identifier, and it's not the full chemical representation. And this is actually what I would like to talk about today, because there are a few implications you may not be aware about that we have in our discussions, and that may give unexpected results if you just come from the pure chemical representation point of view. Okay, a little bit more about the timeline. First version released in 2005. The most important one is the 104 release in 2011. What you see in between are changes of the ownership. The InChI as an international chemical identifier moved over to the IUPAC, so nowadays it's called UPAC International Identifier. And with the other part was that the financial part had to be set on a broader base. So if you've got an IUPAC project, you get just some money, about $10,000 to develop something new. The money is just nice to have meetings of the groups being involved, but you cannot program anything. That's not enough. Yeah, and now people look for other financial resources, and a lot of people argued that the IUPAC may not be the best place to put any money into, and therefore they created this InChI Trust. So the foundation of the InChI Trust was pretty important for the financial development of the InChI. And the InChI Trust is mainly run by publishing companies. Yeah, so you've got Wiley, you've got Elsevier, you got Springer Nature over there, ACS, American Chemical Society, represented by CAS, is a member, and so on. What has happened in between? So this 104 release was the first important release that really made it into really broader use. Then we had the 105 release in 2017. We got our Reaction InChI out in 2017. And we have the latest release in this year with 106. And what you see over here is the very big gaps between two releases, and they are really caused by the fact that besides the developer, none of the people are paid, except Steve Feller as the head of the project. And you know, it's just in spare time we have to work on that one, and that delays processes quite a bit. Yeah, so in terms of the Reaction InChI I'm responsible for, we could be ready already 2 years ago, but time leaks just came up to the point that we haven't made that progress we wanted. InChI is used meanwhile in a broader way. We've got examples over here that have been listed by Steve Fellers in his talk that I took over. Biggest one is PubMed. Well, actually, PubChem already is, I think, meanwhile, they have got 130 million as well. EBI, NIH has databases, and even Elsevier Reaxys provide about 60 million structures in InChI format. Plus the virtual databases, so it's part of the genome database with 166 million. And the Xavi project, meanwhile, has got 4 billion InChIs in the database. Yep. The nice thing about that one is they need, especially Xavi needs an identifier that is fast, that allows you to get a straight access for exact identifications, and text string is perfectly, very perfect for that. How that looks like, I think it becomes easier understandable a little bit later. Okay, how is InChI organized itself nowadays? As mentioned, InChI is part of the IUPAC. So we are part of the IUPAC subcommittee number 8. And it's supported by the InChI Trust. Yeah, so to give money into that one. Formally, decisions are taken by the subcommittee. But in practice, a lot of things have to pass InChI Trust first to come up to the real world. And a lot of people are member of both. Yeah, so it's an overlapping part. The InChI subcommittee meets once a month to discuss the latest part issues. The InChI Trust about every 3 months. Yeah, to take any financial decisions, especially. In itself, the InChI is organized in working groups. Yeah, so those are the specialists representing special areas, like, for example, extended stereochemistry. In the current moment, we are pretty much based into standard stereochemistry with up and down bonds. But of course, you know, Wieske-Mohlfall has been introduced in 1999. Extended stereochemistry is nearly 20 years old as well. Meanwhile, there are more requests about that one. So we had to found a group that has started even working meanwhile. And this is very true for the others as well, yeah, that are just listed over here. Each of the groups just develop their opinions about how to develop the InChI any further. And now be aware, that's why I put them together over here in this group. Those groups are really working on the InChI definition as such, which is very dangerous because it may break code, meaning InChI in the current moment has got about at least 65,000 lines of C code. And obviously, this is not something that is easily to be maintained. And with that one, any type of extension or changes, especially in the code, we have to be very, very careful. So beside those groups really working on the format of the InChI itself, we've got working groups that use the InChI. Yeah, so mixtures is a good example, or my part, the reaction InChI. We are just taking the InChI as is, and with all the gaps it has as well, for example, in inorganic and organometallic compounds, but defining our format, how to use the InChI within reactions. And those are the groups just building extensions to the InChI to make it useful, to make it extendable to other areas that are important for us. The latest income to that one are the nanomolecules. And they are a very, very interesting combination where you need mixtures, you need even reactions in there, you need more recipe-oriented description. Yeah, so you see already there are openings into other areas where we have to discuss how to handle that. And not that old as well are the education section and the work on GitHub, where we are going to continue to work on to open the code as a real open source code. Yeah, those are the, this is the InChI ecosystem. And Jonathan Goodman, who is, besides the fact that he is a professor in Cambridge, UK, he is the secretary of the InChI group, developed this graphics. And you see the InChI in the middle, and then all the different layers that are all around. The inner layers are just working directly with the InChI format, and the further out you come, the more it's just using the InChI and combining InChIs into other areas. And this graphics may help a little bit to understand where you are within your thinking. So if you talk about organometallics, you are pretty near to the InChI part. While if I talk about reaction InChI, I'm further out and I have to live whatever InChI delivers to me. And with that one, you come up to another point that I'm pretty interested in the other groups as well, because more or less they contribute into my work as well, because if you change the InChI, my reaction InChI is changing as well. And my means this is a group of 6 people, by the way, so ours. Okay. Next part is, as said already, InChI is an identifier like the CAS number. Yeah, so InChI is nearer to the CAS number than to a chemical drawing from what it is supposed to do. But the InChI is developed as a digital identifier that is taken from a structure. And with that, you see that the InChI as such is pretty near to the structural representation of a compound. The other important point about the identifier is that the identifier has to normalize the structure. And this is something we are going to talk about a little bit later in the example I provided. Yeah, so we have got this issue about normalization. And the other part is that we have different types of InChIs. Yeah, so if you start to calculate an InChI, you have a set of parameters that can be used for very specific purposes. And we have got a standard set out of those parameters that use the standard InChI. Yeah, they are specified. You see the 1S down here. That always means you've got the standard InChI. If you've got a B over here, actually comes from beta, it means you have chosen any non-standard parameter set. So how does those parameters look like? I hope it's not, don't go into the details. But what you see is we've got parameters for input, for output, for the conversion, for key generated InChI keys. And we have a number of things that do handle structural issues. And let me take out the stereochemistry because I had to fight with that quite a bit. The standard settings are that you, in case you have got any stereo bond, up or down bond, you're seeing that one as an absolute bond. Or for people that are familiar with the old MDL drawings, with mole files, they are interpreted as a structure with chiral flag. Okay, I have a problem with direction InChI for that. MDL introduced the chiral flag actually to distinguish between racemic compounds and the unknown ones. And we cannot do that within reaction InChI. Yeah, suddenly, if you've got any reaction that leads to racemate or vice versa, racemate to the pure compound, we have something like A goes to A. Yeah, you see the limitation that come out of using the standard InChI, because if I would use a setting called stereochemistry as use chiral flag, I would already have the chance to distinguish between racemates and the absolute known compound, even without having enhanced stereochemistry. But using this flag means I'm leaving the standard part. And leaving the standard InChI, for us, the decision was not doing that because we wanted to make sure that the InChIs we are delivering are compatible with any searches done by other people. So if somebody looks for a certain product, it's a very typical way that people just use the InChI, and the InChI in that case is the standard InChI. Yeah, so we have to stay compatible with the standard InChI to let other people find a reaction. Yeah, that's why we decided to be against that one. But what you see over here as well is, if you have a very specific usage, like for example, your own in-house database, you are not forced to use the standard InChI. You can set up your own parameters, your own parameter set that makes the InChI most useful for your work. Yeah, that is pretty important for people developing an in-house system, that they know those parameters do exist, and that you may have to play around with the parameters to find the optimal way for your settings. Yeah, and actually, if you talk to the specialists like Evan Bolt, who is responsible for PubChem, you see that they use other settings for their databases. Okay, that is just about the parameter and the calculation part. Now, what I would just like to have a short survey, which may be a little bit difficult because I do not see you, but it's a very, very simple example I'm going to talk about now, but I think it explains a lot how InChI is thinking and what you get out of that. And that's what I would like to do for today, because out of that one, I think we're going to have to discuss a number of questions that we have to take back for the entire organometallic and inorganic discussion. But let's start. Obviously, the nitrile group can be represented in two ways. I just called one A, the other one B. And it's pretty obvious as well that from a chemical point of view, A is preferred. But what about B? Yeah, so it's quite interesting if you talk to IT people, they see differences between A and B. Yeah, and that's true for the computer as well. A and computer in that case means most of the programs we are talking about are graph-based, and those are two different graphs. A and B is not identical from the computer point of view. So typically, if you talk to a chemist, A and B are identical, not an issue. But if you talk to computer people, they say, oh no, they are different. And it's an easy way to distinguish in the discussion what type of people you're talking to, by the way. Okay, we shouldn't talk about what is correct, but the interesting question is what version is used in most, of the industrial databases? And this is A. Yeah, so most of the databases I've seen, they talk about N plus or minus. But now, what version is used within reactors, for example? Nowadays, reaction users, if you start a query, it doesn't matter anymore. But if you export the data, you find out it's B. MDL was part of Elsevier, and with that one, our Cologne office of MDL was part of the Frankfurt Beilstein office. And we had endless discussion about the right way. The outcome was MDL stayed with MDL, N plus or minus, and Beilstein later on Reaxys stayed with the double bonded version. Yeah, so you only see it, by the way, if you do an export of Reaxys data. And for the nitrile group, you have to do normalization to your own standard. Which way you go around doesn't matter, but you have to normalize it. Now the question is, what is happening with InChI? And let's take the example and go a little bit further into how an InChI is set up. The InChI consists out of multiple layers. The first one is actually that is not listed explicitly over here. It's just giving you the version. Yeah, 1S means it's 1 and the standard InChI. 1B means it's a non-standard setting of parameters that has been used to calculate this InChI. You've got the formula as a very important recognition point over here, followed by the connectivity, by a hydrogen layer, by isotopes, stereochemistry, and tautomers, and at the end you got charges. Okay, let's take the example. That makes it a little bit clearer. In our case, it starts with 1S, meaning InChI version 1 standard. The next one is the chemical formula. We don't have to argue about that one. And now you see the connectivity. The starting point is the lower C over here just means we are just talking about the connectivity layer. How to read it? The first atom is linked with the second, sixth atom, second atom, fourth atom, seventh atom, and so on. And then from the seventh, you've got a chain that goes back via 5 and 3 to 6. So this must be a cycle. And from 7, you go to 8, and 8 is linked with 9 and 10. Now, if you see the molecule, one or the other, we're coming back which one it is, but you see already I took a decision over here. You see we have got atom 1, we've got atom 6. Now, whether this is 2 and 4 and this is 5 and 3, it's not described, it's left open, but they are equivalent. You go, in our case, I took 2, 4, 7. From 7, you've got the line back 5, 3, 6. And the number over here is R8 and 9 and 10. How do you get the numbers? Let's start with the numbering. We've got 7 carbon atoms. We've got the nitrogen atom as the 8th one, and 2 oxygen atoms, which are become number 9 and 10. Yeah, so this is pretty clear out of that one. Nitrogen must be the 8 over here, and 9 and 10 are the oxygen atoms. For the numbering of the carbon atoms are based on the Morgan algorithm. So within the Morgan algorithm, you try to identify the primary entry point for this type for any type of compound, by the way. It is pretty heavily used, for example, within the MDL by Jovia line of chemistry. And not only over there, the others do it as well. And so the numbering comes out of the positioning within the Morgan algorithm. And that's what I just described leads to this new numbering, which is independent of the original drawing. This is one of the most important points of the InChI. Yeah, independence of any kind of drawing you have in the beginning. Now, do you see any bonds described? No, you only have the connectivity. You know that atom number 1 is linked to atom number 6 and so on. We do not talk about any bond, but we talk about hydrogens. So we know that the hydrogens number 2 to 5 have got one H atom. 2, 3, 4, and 5 are just at the benzene ring with one H atom. And then the hydrogen number 1 has got 3 H atoms, which is the methyl group. That means bonds are not described directly, and this is and by that, this format is distinguished from other formats like SMILES or MolFile. They are described indirectly by listing the number of hydrogens you have at the certain positions of the atoms. Yeah, it's a completely different thinking, which makes it easier, for example, to handle tautomers, because now you can just say hydrogen is linked, is related to following positions and so on. Yeah, this is one of the nice outcomes of not having any explicit bond order within the system. Okay, that is a way to explain a simple InChI. Of course, if you've got large molecules, it becomes quite extensive. And in the current moment, the metal atoms are not handled within the connectivity at all. Yeah, so the standard InChI, well, actually InChI in general leaves metal atoms alone and just lists them. Yeah, that is a long discussion, and I wouldn't like to do it today. Not to let us come back to some discussions about the details over here. Okay, a few notes about that one. The primary input and output format for InChIs are mol files. Yeah, so at the end, so the V2 mol file is fully represented. The V3 mol file we are working on, like for example within enhanced stereochemistry. But for example, the V3 mol file is already used to handle large molecules who have got more than 999 atoms or bonds. And other parts of the V3 mol file will be implemented stepwise with further releases. The other way around, you can export InChIs into mol files. Yeah, so you can transfer mol files into InChIs and vice versa, InChIs into mol files. And if you do so, in the very first step, you just get 0 coordinates. And what is left is the molecule down here. Everything is just on top of each other. You have to extract the molecule and have to expand everything. Normally, this is done just by cleanup programs. But it has one interesting effect. The InChI keeps stereo bonds and that information. But if you expand the atoms now, you're not sure whether you keep the R or S order at a certain center because you just re-expand it. And that may lead to changes in the stereochemistry. And on the other hand, I just forgot something to mention before I continue over here. Because we do not see any explicit bonds over here, the easier way to do a normalization for the InChI is using the false nitro representation, so the double bond one, because you do not have to give the N plus or minus part into the explicit InChI. Yeah, it's a shorter way to represent the structure. And the thinking behind that one is we are an identifier and we do not want, we do not take care so much that we fully represent the chemistry behind that one. We have to make sure that this chemistry is uniquely identified. Yeah, and that's why the InChI may use the false nitro version without having any problems to be used. Okay, but nevertheless, if you want to come back, you would like to have the original information. Yeah, this is important for the stereochemistry, as mentioned over here. This is important to get the right nitro group. And therefore, we find the so-called auxiliary level within the info, within the InChI, the so-called Aux Info. And now what you see over here is that you keep all the original information that are available. For example, in this section, you have got all the coordinates that have been linked with the original atoms. And because I just had those ones in two different sections of my drawing tool, you see they've got different coordinates. But more important over here are the blue, parts that are marked in blue. Over here, you keep the N plus O minus, while you've got the NOO here. Yep. With the Aux Info representation, you are always able to return to the full original structure as drawn and as taken in. Yep. That's why the Aux Info is very important to make sure that you really document what has been taken for the reaction InChI, for the InChI calculation. And this may be very interesting, for example, within database use, where you have to document something. Yeah. There's one more InChI available, and this is actually the one that is mostly used, that is the InChI key. If you, and now I have to step back, the InChI, as said, has got multiple layers, and those are the layers, the main layers that construct the InChI. Basically, the first three layers are hashed together in the first set, and those layers are hashed in a second set, and this is the third set, the charges. Now, coming back to our InChI key, you see we have this hashing algorithm, and you have this longer set of hashed characters that represent all the three first layers I just mentioned. Then you have got this one. The blue one actually means we do not have any stereochemistry over here. We do not have any isotopes over here. Basically, the Ufahoy means it's the hash for, it doesn't exist for nothing. And because we are working with standard InChI in that case, and we are just working with version 1, we have got an SA at the end. And be careful if you're just talking to any InChI person and she calls you an Uferhäuser, you are just nothing of the first version, standard nothing of the first version. You may react to that one. Last but not least, the N means the molecule is neutral. Yeah, so L means, I think it's 1 plus, and the M, no, M is 1 plus and the O is 1 minus. So that you have the full total charge described over here. It's pretty obvious that this Uferhäuser /N really occurs in a lot of those InChI keys. And it's repeating pretty often because most of the information in terms of connectivity is described over here. With the fixed length, it has a number of advantages. Yeah, so first it is used just to compare different structures pretty fast. It is used for searches in the web because this is a string, and if you start, and it's pretty unique string as well. And if you put that one into Google, for example, you immediately get any providers of the compound. It can be used as an identifier within the database because we only found very, very, very few hash clashes, and it may, I think, all of them occur in the area of long peptide sequences because they have problems in the stereochemistry where this part is not Uferhäuser anymore, but it is just the compressed representation of the stereochemistry and has issues in very rare cases. Actually, Jonathan Goodman on his website is collecting the cases, and I think he's got 3 or 4 cases, something like that. With that, you see that especially the InChI key has got a very strong, very high importance for chemists, even on the bench, because if you're just looking for a compound, where to buy it, just create the InChI and send it around, and you get some offers in a lot of cases pretty immediately in your browser. So with that, I would just like to give more overview information at the end to let us discuss where to find information. One way is to go to the site of the InChI Trust. There you find videos as well, giving introductions into InChI. On the other hand, of course, you find the UPAC webpage, where you get some more information about it. And last but not least, thanks a lot for the invitation to the Stammtisch. And the number of people really working on the InChI, if you just count all the groups, I think we must be 100 or so. And of course, if you've got more questions, please send it to me.